Hey everybody, this is Mr. Beckstrom, and today I want to take a look at an example from section 4.5 on optimization. This is a pretty hard section. Some of these questions get extremely involved. Some of them are pretty difficult to follow, so you're gonna. I gave you 5 days for this section, so make sure that you're walking through these problems and really trying to understand them. I'm going to do part A, and I'll let you try to do part B. Remember, they have the question help there to kind of walk you through some of these, but I just at least want to try to kind of give you an idea of what we're doing here. Alright, so this one here, it says a boat on the ocean is 4 miles from the nearest point on the straight shoreline, so right here. That point is 7 miles from the restaurant on the shore. A woman plans to row the boat straight to a point on the shore and then walk along the shore to the restaurant. And then they want you to complete parts A and B. So we're going to do part A, and it says if she walks 3 miles an hour and rows at 2 miles per hour, at which point on the shore should she land to minimize the travel time? So here she can boat 2 miles per hour here and then walk 3 miles per hour there. She can boat 3 miles per hour here and then walk 3 miles per hour there, or 2 miles per hour here, then walk 3 miles per hour there. She can boat the entire way. So she's got a lot of options. In fact, she's got really an infinite number of options here. So we need to write some type of objective equation which is going to kind of describe the ways in which she can both row and walk, and we need to do it in a way that describes the amount of time that it takes her to do that. Now remember, we're talking about distance, rates, and time, and distance is equal to rate times time, right? So that's just kind of one of our normal formulas. So distance is equal to, so in other words, if you're going 30 miles per 1 hour for 5 hours, the time cancels out, right? So using this formula here, since we're trying to go for time, just divide both sides by the rate, and you're going to get what? Time is equal to the distance over the rate. The distance over the rate. So this is how, since we're kind of solving for time here, we're going to put our rowing and our walking as distance, the distance it takes over their rate, over these values here. So our objective function should look something like this. So here's our objective function, and that's going to equal, so how what is the distance that's going to take to get from here to here? Well, it's going to form a triangle, right? Where we have to, or where this leg of it is going to be 4, and depending on where we land, so let's just kind of make a, let's say we go like right here, then this leg is going to be some length. Let's call this leg x here, right? And so this distance that we travel is going to be the hypotenuse, right? So we're going to be traveling, let's call this distance y. So y is just going to be the square root of x squared plus 4 squared. Plus 4 squared, right? So this is going to be the distance that we travel on our boat to the land if we call the distance from the nearest point on the shore and wherever we land that x. So that's going to be the distance of our boating. So that's going to be, we'll call that square root of x squared plus 16, x squared plus 16. And remember, we have to put that over the rate. So for, it's kind of a bad 16. Let me write that 16. I look like a 15 over 16. Then the rate for rowing is 2 miles. So I'll just put it over there, 2. So that's our rowing part. And then we also have to add in how much it's going to take to walk. So the amount that it's going to take to walk, let's say we land here. Well, it's going to take 7 miles less whatever we landed here, so less x. So it's going to really just take 7 minus x. So that's going to be the distance it's going to take to walk. So if we go straight to shore, it's going to take us the full 7 miles, because that means our x is equal to 0, so 7 minus x. If we go straight to the place, that means our x is 7, so 7 minus 7 is 0. That means we walk actually 0 of it. So it's going to be 7 minus x, 7 minus x, all over, and over the rate, which is 3. So this is our objective function here. This is the function that we're going to try to optimize, we're going to try to get the best possible time. We're going to optimize the time. And the way that we're going to do just about all of these is that we're going to come up with some type of function that describes however we're going to do what we're going to do, whether we're going to optimize the size of a square, the size of a cube, the distance traveled, whatever we're trying to optimize, and then we're going to find the first derivative of it, which is going to give us some type of graph of this optimization function, which we can then find the critical values of it, because the curves in this graph, or the peaks and the valleys, are going to represent highs and lows of it. So if we can identify those and then check those are going to tell us the high points and the low points of where these values occur. And that will give us the what we're looking for, pretty much. All right, so now we're going to find the first derivative of this function in order to find those critical values so we can check to see where they are. But before we do that, we really need to describe the limitations, or or sometimes they call it the domain of our x variable here, or our independent variable in this case. And that is, what are all the possible values that it can be? Well, if we took the boat straight there and we walked the entire way, at most we're going to walk 7 miles, right? And at least we're going to walk 0 miles if we go. So it's going to be between 0 and 7 there. And if we took the boat all the way there, right, that's the hypotenuse there, which has to be greater than 7. So there it's between 0 and whatever that is. It's the square root of 4 squared plus 7 squared, which is bigger than 7. So we have to use the smaller of the two, because we still can't go more than 7. So our constraint, or our domain here, is going to be between 0 and 7. Now, why is this important? Because when we get our values at the end, when we get our critical values, we want to make sure that they're between 0 and 7, because it doesn't make sense to have any negative values, because we can't go a negative distance. And it doesn't make sense to have any values that are bigger than 7, because there's no possible way that we can walk more than 7 miles, right? We're not landing anywhere over here. And there's no possible way that we can, yeah, that's pretty much it. All right. So let's work on finding the first derivative. It's probably actually the hardest part of this problem. So I'm going to first rewrite this in a derivative-friendly manner. So I'm going to pull the 2 out as a 1/2. Write this as x squared plus 16, like this, to the 1/2. Get rid of that fraction. And then this is just going to be plus 7/3 minus 1/3 x. Right, just kind of separating that fraction, which makes it a little bit easier. So when I find the first derivative here, just use the chain rule here. So that's going to give me a 1/4, and then I have my x squared plus 16 raised to the negative 1/2 times the derivative of the inside function. Right, that zeroes out. I'm just left with a minus 1/3. Cleaning that up a little bit. 2 cancels out there, so I'm going to be left with an x on top, and on the bottom I'm going to have a 2. I'm going to bring this down to the bottom because that's a negative exponent, so that's going to be x squared plus 16 like this, and minus 1/3, right? So double check that math there, but that should be right. So this is the derivative here. I should put a little mark there to show this is the derivative. All right, so here's the derivative of our objective function there. And what I want to do is I want to set that equal to 0. So kind of running out of space here, but if I do that, if I set it equal to 0 and then I add 1/3 to both sides, I'm going to kind of try to save myself a little bit of space here. So I have x and x squared plus 16, and then that's going to be equal to 1/3, right? So I just set this equal to 0 and then added 1/3 to both sides. Now I cross multiply and I'm going to get 3x is equal to 2 x squared plus 16, like this. Go ahead and square both sides, so I get 9 x squared is equal to 4 times x squared plus 16, like this. And distribute that, so 9, get close here, equal to 4x squared plus 64. So 5x squared is equal to 64. Almost done, almost done. Come over here. I'm going to get x squared is equal to 64 over 5. And finally, x is equal to plus or minus 8 over the square root of 5, right? So here's what I have, and then I check to see which ones of these are in my original domain and just the positive version. So that's the only one. And so this is my critical value. So that's the one that I'm going to use. And I also have to actually check my endpoints as well. So I check my endpoints and I check this value to see which one is best. So let's go ahead and do that as well. Alright, so I just took this equation here, so that's what, 1/2 x squared plus 16 raised to the 1/2 plus 7 minus x divided by 3, and I'll go ahead and use my table and check those values there to see which one gives me the lowest time here. So second table, so I can put a 0 in there, and it's going to take me 0. It takes me 4.333 seconds. If I put a wait, is that right? Hold on just a second. All right, yep. And then 7 seconds, that's the other endpoint, and I get a 4.03111. So this says that if my x value is 0, which means what? That means I boated straight to shore and walked the entire way. It's going to take me 4 1/3 seconds. If my x is 7, that means that I boated the entire way because my distance there was 7 where I landed. It's going to be a little bit shorter of a time. Now let's put in the 8 divided by square root of 5 and see what I get. See if I get a better time there. So 8 divided by second square root of 5. And sure enough, so that actually gave me a slightly better time, and that is about 3.5777. So that's right, that's close to the middle there. So that's somewhere right about kind of where they had their red line. So it's actually most advantageous in this point, in this scenario, to boat somewhere around the midpoint here and then to walk the rest of the way. Alright, I hope this helped a little bit. I know this is a longer than normal video, but if you have any questions, let me know. The second part to this. Part B is pretty similar, except for I think for one of the rates, instead of I think for the rowing rate, instead of 2 you put in an S, and then you kind of do the same kind of thing when you do the derivative. You just have to use an S. So you anyways, but try it out, see how you do, let me know. Thanks.